Welcome back, everyone. We're going to talk about one of the most important things that this class is about, convex sets. And after that, we're going to talk about convex functions. So let's just start with the basic definition and also talking about why it's important. Easiest definition is by picture. We'll write the algebra that relates to this picture. What's a convex set? It has a requirement that any 2 points in the convex set, if I were to join them by the line between them, and note, of course, I'm always drawing in 2 dimensions because that's the best that I can do, but this is a general idea that extends to higher dimensional sets. So a set is convex if for any 2 points that I draw, the line between them is also contained in the set. So we can easily draw sets that are not convex. So for example, anything like this, you'll see that while it is true that for some set of 2 points, the line segment between them lies in the set, there are other 2 points where I have to go outside if I'm going to draw them by the straight line. Let's translate this picture intuition into algebra. It's actually quite straightforward. If I call this point x1 and x2, how do I parameterize the points in between? Well, any point in between is some combination of x1 and x2 with weights that are between 0 and 1. So the definition says a set C, which is a subset of Rn. I'm also introducing notation in case you're not familiar with it. This symbol means subset here, and Rn means a set of means n-dimensional space. Is convex if for any points x1 and x2 in the convex set, and for any possible weight between 0 and 1, the intermediate point, lambda x1 plus 1 minus lambda x2, also lies in the set. So the writing on the left is exactly expressing the intuition on the right, but we've freed ourselves from any kind of setting where we need to be able to visualize the space. So we can think about it in a more arbitrary, abstract context. So why is this important? The rough idea here, which we'll see again in more detail later, is quite simple, and it's as follows. Suppose that your goal in your life is to move as far as you can in this direction. Well, suppose that your constraints happen to be this convex set. What are you going to do? You're going to move in this direction until you hit a wall. And then you'll see that actually you can, let me redraw this set to make it a little more obvious that this is where we want to stop. Because actually here you can see that if you move here, the way I drew it, it's slightly, ever so slightly further in the direction that I drew. So it will help to make it a little more clear that, that this point is the stopping point. So if this is your convex set, what are you going to do? You're going to move, you're going to hit a wall, and then realize that while you'd like to go further, you can't do it. And that's all you need to do. If your set is convex, you don't have to know something about what is on the other side of that wall. On the other hand, if we were living in a world where the set were not convex, so now let me redraw this. I'm going to take this away. Again, we have the same objective in our life, to move as far as possible in this direction. But I'm going to draw a set that's not convex. So we're restricted to a set like this. So what do? You move, and you hit a wall. And you might quit. But if you quit, you're missing out on all of these great points over here that would get you further in terms of your goal. So this is exactly why intricate mazes are hard to solve, because we need to know something global about the structure of our constraint set. But for convex sets, if we hit a wall, we know that's life. That's the best that we can do. So we're going to see this in more detail as we move on. But this is roughly why convex sets are important. I'm going to define a few convex sets that we're going to be needing a lot. A subspace, if you recall, is the set of points that are closed under addition and scaling. But there are several ways that we can define a subspace. let's first define it as the span. If I have vectors v1 to vk, remember that the span of these vectors is defined as the set of all possible linear combinations of them. In other words, it's the set of vectors v such that v is equal to the sum of alpha I vi for some scalars alpha I. Another way to write this is, so let me name this vector space V. So note that V is also equal to the range of the matrix A, where A is made up by stacking these columns V as columns. So this is one way that we can define a subspace. So there's an alternative way that has to do with the other main property of matrices that we've defined, which is called the null space. Remember that the null space of a matrix A is defined by, and I don't want you to think that, maybe I'll change this name here so we don't necessarily think that this is the same matrix, is the set of all vectors x that get mapped to 0. So this is also a very natural way for us to define a subspace. And an exercise that, if you want to make sure you understand these definitions well, I would recommend is check for yourselves that for any matrix A, the range and null space are indeed closed under scaling and addition. In other words, check that these are indeed subspaces. So this is, the null space is another very natural way for us to define a subspace. And why is this something that we've been used to thinking about for quite some time? If you think back to early days when we define a line, so how do we define a line? Y equals ax plus b. This is our slope-intercept formula. If this is x and if this is y, then this would be my intercept b, and this rise over run is a in this example here. But really rearranging this, you can see that, that this is a relationship between a and b, between x and y. So this is, in fact, very similar to this form that I've written here. It is equal to, so I can rewrite this as 0 equals a times x plus minus 1 times y. Actually, let me put b on the left-hand side. So another way to write this in vector notation is the matrix, if you want to think of it that way, as a minus 1 times the vector xy equals minus b. You see, this is very close to this null space definition, except I don't have 0 on the right-hand side. And that's because this line is not going through the origin. If it were going through the origin, then b would be 0, and a line would exactly be a subspace. That's defined using this null space property rather than the range property. So why did I write this with an offset? This is the second part of the title, an affine space. So you see that this is a subspace is exactly the same as an affine space, except it's offset by 1. So one of the things that we're going to be seeing repeatedly in this class is subspaces and affine spaces defined actually in both ways, but we're going to also see them quite a bit defined in this null space way, exactly because we care about lines in 2 dimensions. We care about flat planes in 3 dimensions, and we can't visualize it, but we care about the analog in higher dimensions. So let's move exactly to that and generalize what we just saw, but not for 2 dimensions, but the general case. So what we saw is that in 2 dimensions, in other words, in R2, in our notation, a line is defined by, I'm going to write this a little bit more generally than I did before, S transpose X equals B. What was S and B in our example in the previous slide? In the previous slide, S was equal to, I've forgotten, let's look again, A minus 1. A minus 1. X was not a vector, it was X and Y, where those were scalars before. Hope this isn't too confusing to see X and X here. I hope you see what it's clear from the context. And B was, well, maybe it was minus B again. Hope that's not confusing. Okay, so this is indeed just a generalization of that simple example, but it now has the advantage that we've freed ourselves from coordinates. We don't have to think about x1 and x2 or x and y. And this is just a dot product. A dot product is defined in general. So this is, in fact, so in n dimensions, this defines, okay, let's pause for a bit to think about it. Does this define a line, or does it define something else? So let me leave this blank. Right, let's make our cliffhanger here. And this means S transpose X equals B. So to be more precise, what I'm trying to define is all the points X in Rn that satisfy this relationship. So if you're in 3 dimensions, does this define a line or something else? Give you a second to think about it. You can pause. So what this does is it takes away 1 degree of freedom. In our 2-dimensional example, without any constraint, without having to satisfy the line, you can be in 2-dimensional space. But a line restricts you to 1 dimension because it has removed 1 degree of freedom. It specifies one relationship between x and y. This case, again, however many coefficients you have, 3, 4, 10, n, it just takes away 1 degree of freedom. So it's actually not a line in general. It's something that is 1 dimension less than full dimensional. So this is, to introduce you to a little bit of jargon, it's called a hyperplane. And it's just the generalization of a surface. So a hyperplane in 3 dimensions is just a flat space. Like the floor is a hyperplane. The wall or the ceiling is a hyperplane. In 4 dimensions and above, I'm not able to picture it. Maybe you can. But it's the same exact idea. To introduce you to some other jargon here, sometimes this is also called a codimension 1 space. And why is that? Why is it called that? Because rather than having to specify that we're n minus 1 dimensional, initially we have n degrees of freedom. This is one equation. It takes away one of those. We're left with n minus 1 degrees of freedom. So codimension 1 is the same as saying n minus 1 dimensional. It's saying we've removed 1 degree of freedom. So this is a hyperplane. If B is equal to 0, then it goes through the origin, and it's actually a subspace. The reason that this is important for us is that it's going to allow us to define a half space. So it's going to allow us to cut n-dimensional space in 2 with this flat shape. A little bit of other jargon here that's important to mention. S is the normal vector. And it's a normal vector because it is exactly that vector that points perpendicular to the subspace. So let me give you an example back in 2 dimensions where we can visualize things and we can draw things. Let's take the easiest line, the 45-degree line through the origin. So what is this line? How would we define this line? Well, the slope is 1, and the intercept is 0. So if I were to use my point-intercept form, I would have the equation y is equal to 1 times x plus 0. Okay? Or in other words, to write it in my notation here, I would have 1 minus 1 transpose xy equals 0. B is equal to 0, S is equal to 1 minus 1. Let's draw 1 minus 1 and see. Is it the vector parallel to this line? No. It is exactly this vector, which is normal. So this is called, again, the normal vector. And let me take a crack here at drawing in, that's not going to work. Here's my attempt at drawing a plane in 3 dimensions. The normal vector is uniquely defined, and it's that one vector that's perpendicular to this subspace. This would be the normal vector. Now, how do we define a half space given this? It's actually quite simple. Once we've defined a hyperplane is defined by equality. I'm basically just copying down what was on the previous slide. So a hyperplane is all the points x in Rn such that S transpose x equals B. Well, a half space is just everything that's on one side of it. So if I call this thing H, whoops. There we go, there's always a solution. If I call this thing H, and while I'm at it, I might as well write down S and B, because these are the two things that define the hyperplane, the normal vector and the offset, B. Remember, B is a scalar, S is a vector in the same dimensions as X. Then a half space, there are 2 half spaces, which we can just call S, HSB plus, which would be all X in Rn, such that S transpose X is greater than B, and H SB minus, which is exactly what you think it is. Everything. It's the other side. These play a fundamental role in convex optimization for reasons that will become a little bit more clear later, but we can draw some pictures that give us the basic idea. A few slides ago, we defined a convex set in terms of points inside of it. They have to satisfy this property that any 2 points, the line segment between them, is also part of the set. But you'll notice that I can carve out any convex set using half spaces. Here I'm drawing half spaces, everything to this side, everything on this half, everything on this half. And if I'm patient enough and draw all infinitely many of these hyperplanes, I'll exactly have this definition of this set. Nothing else, nothing more, but nothing less. Versus a non-convex set, well, you can see that there's no way you can do that. The best you can do is describe basically this set that's going to contain the shaded region in addition. So this is going to play an important role for us. There's 2 more definitions that we need that are going to be important to us. A set K is called a cone if whenever x1 and x2 are in K, then any alpha 1 times x1 plus alpha 2 times x2 is also in K for any values of alpha 1 and alpha 2 that are greater than or equal to 0. So 2 things you should check for yourselves is, first of all, this does not mean that it's a subspace, and that's just because we're not allowed to add negative values. But on the other hand, any subspace certainly satisfies this property and therefore is a cone. In addition, since this holds for any alpha 1 and alpha 2 that are non-negative, it also holds for alpha 1 and alpha 2 that sum to 1. And therefore, a cone has to be convex. So let me draw a cone. It's exactly what it sounds like. A cone is all these points, extending on forever. Now I also want to define a polar cone. For K a cone, the polar cone is defined as all vectors that make a greater than or equal to 90-degree angle with everything in the cone. Let me draw it first, and then this is supposed to be a right angle. This is a right angle. So the polar cone is everything here. And you can see that any vector you take, any vector you choose, makes a greater than or equal to 90-degree angle, not just with the boundary of the cone, but with everything in the cone. So let's make this definition. The polar cone, sometimes denoted like that, is equal to all vectors x, such that the dot product of, let me write z here so it's a little bit more clear. All vectors z, such that the dot product of z with x is less than or equal to 0 for any x in my cone. Remember that this is our condition that's equivalent to making an angle that's greater than or equal to 90 degrees. So some more examples of cone and polar cone. So we will use these to characterize optimality. In other words, when is a particular solution to an optimization problem the optimal solution? And we're going to use a specific cone and polar cone, which it's really going to be exactly the same definition as I just gave, but it's important just to give these names and draw a few pictures. So the first is a tangent cone. We should think about the main problem we have at hand. I want to minimize f of x subject to x in my set x. This is the main thing we care about. So let me draw this set x, and we'll draw the tangent cone. So suppose that the set x looks like this. Has some smooth faces, has some round faces. The tangent cone of x at any point in x is defined as basically the closure of all directions you're allowed to move in. So what's the tangent cone from an interior point? Well, I can move in any single direction and stay in the set. Therefore, if x is an internal point, of x, formally if it's in the interior, if x is in the interior of x, then I can move in any direction at least a little bit. So the tangent cone is equal to the entire space. Let's check what we can do if we're at a point on the boundary. What directions can we move in from here? Well, I can move in any direction that brings me into the cone. Now you can see that as I get closer and closer and closer to this tangent at this point, I have to move less and less and less in order to stay in my set. But nevertheless, I can get arbitrarily close to that tangent. So that means that let me label these for x equal to x2, the tangent cone is just the shaded half space, or this half space is the indicated half space. And let's finally look at this point x3, and you can see that in this case, the tangent cone is exactly going to be the cone defined by these two points. Cone defined by the two boundary vectors. So this is the tangent cone. The polar cone is so special for the tangent cone that it has its own name. This is just the polar of the tangent cone. And let's again draw it. Maybe it's helpful if we just use this exact drawing here. Let's see if I can do this. Almost. So this tangent cone. So this is the exact tangent cone we had before. I've drawn all the tangents. So let's. So what is the normal cone for each one of these? Well, the normal cone for an interior point, let me call this x1, x1, x2, and x3. The normal cone of x is all the vectors that make a greater than or equal to 90 degrees to all the vectors, because that was a tangent cone of x1. Well, that's just the point 0. The normal cone at x2, what set of vectors starting from x2 makes a greater than or equal to 90-degree angle with everything in the subspace, with all of these potential vectors? There's only one, the perpendicular vector. So it just equals this vector. Lots of arrows. Hopefully you can see what's going on. And finally, the normal cone at x3, this is exactly like the picture we drew when we were defining the normal cone. Drawing 90-degree angles here. This is the normal cone. So we're going to see how these are used in order to characterize optimal solutions. We'll pick this up in the next session.